Let's start. So, welcome to the undergraduate math program, 2021-2022. This will be our second to last event of this academic year. As one might know, there might be three main branches of mathematics: the algebra analysis and topology, and the geometry. So, these two branches kind of are isolated, but not really, because we can combine these two and just use tools from one branch and apply it to the other. For example, we can have analysis and merge with like geometry, let's say, so we can do calculus on different, geometrical spaces, let's say on a sphere or something. And then that brings up the interesting topic of differential geometry, or other stuff as well. Maybe you can do like, let's say we can find the algebraic structure of like rational points and related curves, and that would be a very interesting topic on its own as well. And you kind of develop into this algebraic geometry kind of stuff. Yeah. And today we'll be learning more about the interaction between algebra and analysis, and more specifically the C-star algebras, or C asterisk, C-star. C-star. Yeah. And hopefully we can learn or see how it's also going to be applied in topology as well, using K-theory. And without further ado, let's have Mathieu.
Everyone. Yeah, it was quite hard to find pictures for those. Can't find pictures of maths anymore, especially in like. Anyway, so first of all, hi, I'm Matt. Quick show of hands, who's a first year, second year, third years, fourth years? No, okay. I guess she covers up for one. Okay, so yeah, C-star algebras. I'm going to spend about half of this just going through a list of definitions that we need to prove anything later on, which I hope will be instructive enough because it covers like a huge broad range. In brief, an algebra is an algebraic structure, right? Remember doing algebra in secondary school, sixth form, whatever, and then eventually, if you're in the third year, you can do things like commutative algebras, right? Which I don't do, so we'll see how I get along with that. But we can start with talking about something slightly different from algebras and go into functional analysis, which will link into this idea of C-star algebra later on, right? So you've all done some linear algebra, right? They're not taking functional analysis. Next year, okay. So let's do a bit of a head start, actually, to cover kind of some of the basics on what it is. Okay, first, we need spaces, right? You know what a vector space is. If you didn't, why are you at university? No, so we're vector spaces, right? And we have norms of vector spaces. I'm assuming your definition of norms, right? So norm being satisfying it's linear, triangle inequality. I'm going to assume you all know norm is, right? A norm. So vector space with a norm on it, right? And vector space can be infinite dimensional. In fact, we're working on the assumption that it might be infinite dimensional, which means we can't do nice things like have bases or matrices. We'll get to the same, right? So vector space with the norm, it's a bit better than vector space, but we want to have nicely behaved normed vector spaces, right? So that's the first thing we introduce. Can everyone see? Read my handwriting, right? And yeah, is something called a Banach space, Banach vector space. Definition is very simple. You have a Banach space is a vector space with a norm, such that the metric associated with the norm, right? So the distance function between 2 points x and y, say, the norm. Right, that's what we call the distance between 2 points, the x of y, right? This is what's known as complete. So in analysis 1, you've done Cauchy sequences, Cauchy sequences. So under this distance function, right? You basically the normal, normal absolute values. But this any Cauchy sequence, right? So just make this xn, this xn and xn converges, right? Pretty simple. the metric induced by the norm converges. Makes Cauchy sequence converges, it's complete. Bounded space is a complete normed vector space, right? We're going to go a little step further to introduce what you all know and love, the dot product or inner product, with a Hilbert space. So Hilbert space is a bounded space. We've added an extra thing. We've added something called an inner product. You recognize it as a dot product in like standard Rn. But it's inner product. It's a bilinear form. It's linear in the first term. You know, it has a property this xy is yx, so it has a symmetric conjugate. The symmetry is the complex conjugate. Of course, we will be working mainly over C, a vector space, complex vector space, right, rather than real vector space. But we will, in a bit, be talking about general vector space as general things over fields and actually rings even. But a Hilbert space has this, right? And of course, you remember that the inner product of the thing of itself is twice the size, the norm, right? And what we want is the Hilbert space with the inner product, which you choose, right? And the norm, which we can define like this, or taking the square root, to be a Banach space, right? So the norm makes everything converge, right? So these are two spaces you'll find a lot if you do anything functionalities, PDs, or even ODs technically. Yeah. And it's very good because if you assume second year, was it methods for? I think methods for something like that. You'll find these very useful things. Pretty interesting as well because they have nice properties of convergence, which means that many theorems you have in functional analysis use these. Okay. So spaces will be using primarily using Hilbert space, which will denote as H, just H, for Hilbert space, right? Now, you guys remember functionals on vector spaces, right? We can also have operators, which go from operators A, not A, for example, F, say F from a vector space to another vector space. In fact, these will be any Banach spaces which we want to normally want it to be convergent, but even if it's only a norm space, this works. So this is a operator is a linear function from a vector space to a vector space, right? If y is R, you've got functions of your space. Now, this is not necessarily well behaved. You can have annoying cases where things go terribly wrong, like you probably will do this at some point if you haven't already, but the differential d by dx, continue the differential functions form a vector space, an infinite dimensional vector space actually, but vector space nonetheless. But the differential of vector space can be very badly behaved, especially not the way you think. It's still be continuous, right? But you've done things like you take differentiable functions, right? Take a sequence of them, right? They won't necessarily converge to a differentiable function. So a continuous function don't necessarily converge to a continuous function in a sequence, right? Which is annoying because we want y to be Banach, right? And if this thing doesn't work, then it doesn't work out very nice in aspects. But most things are fine, just multiplication. If x and y are finite dimensional, then matrices work very well. We wanted to find some sort of continuity on operators, or the names continuous and bounded are identical. Bounded because what we want is for this operator here to have the property that for on x, f on x, right? The norm of that should be bounded by some constant times x, right? This is what we define as the bounded function, such that if, for example, we want this so that if you grow x a lot, you don't want to surpass this. It just won't be well behaved. It gives all sorts of behaviors. It actually allows for convergence in F. So if you've got an F convergent sequence, N, it will be Cauchy if it's this. If not, it doesn't have to be. You can take the differential operator actually as an example of something which doesn't behave very well. Because you can have like a function which goes really high up at some point, right? And then the differential will go far higher than that. And if you increase it a certain amount, that constant, it will increase it. But anyway, continuous function, just definitions. With continuous function, I'm not going to digress this time. I probably wouldn't digress too much. A continuous bound function is a function which satisfies this, right? And actually, we can define further a best bound constant for C, right? We'll take all C such as this works, given some function, right? All C, take the infimum of the C, right? Smallest C possible, and the infimum of any C such as this, right? Is what we define as the norm of this. Because, as you may notice, function, you've got a space, you've got a dual space of functionals, right? The dual space forms a vector space, but the space of all linear operators between two spaces, L, X, Y here, also forms a vector space. That's pretty easy to check, right? Because of the linearity of the functional, right? You can add two, it's adding pointwise, multiply by constant, multiply by constant actually. And we can define a norm here. So the infimum of this, there's another way to define it would be to be the supremum of f of x, f on x, as x equals 1. You can also that x is less than or equal to 1. There are many ways to define it. This is actually the one we use a lot. It's just the highest possible constant, such that this would hold. Now, as mentioned before, some functions are bounded. So we define b of x, y as the set of bounded operators, sorry, from f to x, x to y, right? And if x equals y, we should denote this as b of x. Okay, this is a nice thing. It's actually closed in the set of operators. The set of bounded operators is closed in the set of operators. We actually go further and define something which has nice convergent properties called the set of compact. Let's bring it out. Set of much better, isn't it? Compact operators, x to y, which is again a function of operators from x to y. There's several ways of defining what makes a compact operator. Technical definition is you take any bounded set, then its image will be relatively compact. If you know what that means, that's fine, because the best definition, I think, is that you take a convergent sequence in X, then you apply your operator, when your sequence, you get another sequence, right? And the operator F is compact if there exists a convergent subsequence. So compact operators actually behave nicely, and we'll see further on they have some very interesting, nice properties with what we're going to discuss about algebras. But those are the preliminaries we need for the functional, the analytics side of things. Okay. You guys know what a ring is? Yeah, ring. Yeah. So first, algebraic definitions. Done algebraic definitions. Def. Are they a ring? We call an associative algebra. This is set A, which is at both times the same times a ring and R module. You know what a module is? It's a vector space. But instead of having a field, real complex, you've got a ring. Or on modules.
Yeah, both ring.
I mean, it's just it's a vector space, but all the conditions you have in vector space which follow from it being a field, right? Like an identity on the field, which you don't have necessarily in a ring. No, multiple inverse or another, let's say, must be a ring. Yeah, it's a topic in itself. Just trust me when I say this. We will be working mainly with R is some fields, right? That will be a vector space rather than a module. But the definition is that it's a module over R being a ring, right? Another thing we need is that so a ring has a set, it has an addition and a multiplication operation, and a module has an addition operation, right? And a multiplication by scalar in the ring operation. We want that the addition operation for the ring is the same as the addition operation for the module, right? So you add things together, it behaves like it should. Of course, you notice that when you multiply it by a constant, you still want it to be in A, because a module is closed under scalar multiplication. So while these aren't necessarily equivalent, they are equivalent when multiplied by scalars, right? And scalars have to be in the ring. Yeah, just like that. Additional property that we need, of course, is R be a scalar in R, X, Y, A is Rx. So the scalar multiplication, this is ring multiplication, this is vector multiplication. Y equals X, Y. So we want to kind of behave like it should, because when you multiply, yeah, so this is how it would be in a field. But it doesn't feel. No, so we just want this, it's a very nice property, which is defined associated R algebra. Now, we're going to take, now we ignore everything that's about modules now, because we're never going to do that again. We want R to be a field, right? Which is going to be really the reals or X one non-immediate field rate that works. But real or complex, we're using complex most of the time. We'll take that, so this becomes a vector space. And as I said before, a vector space has a norm. Can have a norm. If it has a norm, if it's a norm vector space, we call a Banach algebra. It's just an associated R algebra. So A, R, A, whatever you call it. And this is an R algebra, or F algebra in this case, with the property that the vector space you get from this is a Banach space. A very easy property you can deduce from this actually is that the norm multiplying any two elements, right, multiplying with the ring, is less than equal to the norm of each. This is something which everyone hopes they had in their, what is it, analysis 4 exam, because it's just so nice. But it doesn't hold. Anyway, because you can't multiply things out of your vector spaces. You can, this is the ring. So this actually holds if you define it as a Banach space. I'm going to have to omit a lot of proofs here because I don't have so much time. But trust me, look it up if you want. Okay, now we can get to the start of the show and define what a C-star algebra is. I've got more or less definitions out of the way. What's associated R algebra? Sorry, I just don't want to keep it running because my handwriting is borderline legible. I'm trying my hardest so far. Can you read it?
Yeah, it's okay.
So, C-star algebras. C-star algebras. Now, C, as you may not be entirely sharp to know, stands for complex. brings this algebra is a Banach algebra, right? Algebra with a function which takes x, so a, we're using a for algebras from now on anyway. A function which takes x to what we'll call x star, right? Such that this function has the following properties. It is an involution, regardless of the involution. There is involution, which means that x star star, right? So you take the function twice on it, which is just x star, star taken on twice equals itself, right? It has linearity. So x star plus y star, and also linearity. We're doing this over C, right? So the field is C. C's algebra. Lambda here is complex constant. Then the involution of this is the complex conjugate of lambda times the involution of x, right? So that's the linearity. Notice that anti-linear actually. Linearity here and that. Probably 3 is that multiplication of xy equals multiplication y involution thereof equals y star x star, so versus the order in multiplication. Now these 3 here are enough to call this a star algebra. So you can do so R as well, because that complex conjugate is itself. It's called star algebra. The C star algebra follows from the fourth property here, called the C star identity, doesn't write bigger. This identity, which goes like this. The norm, so we have norm now, of x star x equals the norm of x times the norm of x star. It also handy happens that this equals the norm of x star squared because these end up being equal, but that's actually surprisingly non-trivial. And not too hard, but non-trivial nonetheless. This is also equal to more x star, all other properties, but from this you can derive the rest and the properties. But it's called C star identity. It what causes C star algebra to work and sort of makes it have all these interesting things we're going to find out.
What's after the in the box? What's after the first sequence?
Sorry, after this.
Yeah.
So x star norm of x star x equals norm of x times norm of x star equals norm of x star squared, because actually x star norm of x star is equal to the norm of x star. Norm of x is equal to norm of x star. And yeah, so you just flip them around, the norms are all equal. Now you will have this property actually, especially that an operator which swaps them around. You might have seen somewhere, I suppose, because an example of this algebra which you've all seen is M on C, sorry, M on N of C, the space of N by N complex matrices, right? And the involution in this case is just the complex transpose. Actually, yeah, the complex transposition, matrix N to star transposition conjugate. And you can see that this follows, two complex transpose is this, linearity follows, complex conjugate follows, this we know, and this also follows reasonably easily because, I mean, we haven't actually taken a norm on this set, yeah, but we can just assume it's the operator norm. We find it pretty easy because a matrix is just a linear operator, right? Matrix on C, this matrix, again, F, this is just a function from, yes, it's not an operator which takes a Cn to Cn, right? Cn to Cn. Yeah, matrix just takes the integer Cn, and it has a norm we define as, again, take X. If this is bounded and all matrix is bounded, we should take the infimum of this for all X, right? We must restrict it to X. Circle. But this is an example. There actually happen to be two other examples we mentioned earlier, which are BH, the set of bounded linear functionals, and set of compact linear functions or linear operators. Both these are C-star algebras, which isn't too impressive by itself. You just define it a certain way. This is where the link really starts coming along. Of course, in this case, we haven't actually defined what an adjoint is. And I think algebra 3, you define what that adjoint is more or less. In basis, it's on H, so we have then a product. You have some operator F, right? And an adjoint is just another operator, F star, which satisfies this property. We've seen it before someplace, yeah, we'll see it. Hopefully, you can prove this always exists, which is good because that means we can define it on the entirety of our space H. And same thing goes for this, same thing really. But this is an evolution. You can really show it solves all properties here. It's pretty standard stuff. This one is hard. Of course, we're giving an example of a thoroughly analytic type thing, right? On an algebraic term. You may wonder why, how it has ring structure. You notice I wrote B of H and not B of H to another set, right? So because I only wrote one of these, the functional goes from H to H. Because otherwise, something like this, FG, wouldn't make much sense if you took arbitrary things, right? FG, the multiplication, right? It's just normal pointwise on X equals F of G of X, value to G, value to F. It is a ring. It's a vector space, it's norm, it's back, it satisfies this. These are algebra. Okay. Of course, when you have any sort of algebraic function, you want to define a homomorphism on it. Because you really do, okay? Most proofs involve some sort of homomorphisms eventually. Called a star homomorphism, or a C star homomorphism, also works out. But if you don't see if you're on an arbitrary R, but star homomorphism we don't need to see because properties are identical. It's got a star homomorphism. It's a normal ring homomorphism, right? So just quickly, star homomorphism pi from this is algebra A to algebra B is one with additive linear, so lambda x lambda. Homomorphism.
Pi x plus y.
Okay. Yes, trivially. Sorry. Pi x y, there we go. To rectify any states here. And pi of x times y equals pi of x times pi of y once, because the ring structure. And additionally, the reason it's a star homomorphism is the property pi of x star equals pi of x or star here. So the adjoint function, joint property is preserved under homomorphism, a star homomorphism. Pretty interestingly, I mean, I don't know how to prove it. I probably try to prove it, but right now I can't remember how to prove it. That because this, as you can see from this, is a linear functional, a linear operator, right, between these two vector spaces. We can define the operator norm as we did beforehand, and it turns out the operator norm of pi is less than or equal to 1. Which actually means that this homomorphism is contractive. So as you go between here, it's you know, ring pi won't increase the size of the elements. So of course, pi less than or equal to 1 means that pi of x is less than or equal to x. So it's a definition of the operator norm. Spot here. Yeah, that's the star homomorphism. Couple of properties. If it's injective, it's an isometry. Kind of follows from this actually, and this. And if it's bijective, we call it an isomorphism, right? C star isomorphism. Pretty cool stuff. Okay, so couple of things. You have x and x star, right? Both exist. You equal x, you x star. If they're equal, if this is equal to its adjoint, right? We call these self joint. So self adjoint, right? If x equals x star, self adjoint. Another thing, if x star equals x star x, it doesn't necessarily have to be commutative, then x is called normal. And we'll be talking about commutative C algebras in a second, but it obviously doesn't necessarily have to be commutative. Obviously, operators don't be commutative, you know, matrices aren't commutative. Exactly so. Subjoint, no. We were talking about subjoint things quite a lot actually as time goes on. Couple properties of subjoint operators. So elements of the algebra in the form x star. Just take an x map to x star. The set thereof actually, first of all, is equal to x star x. But of course, it doesn't necessarily have to be equal to each other. And this forms a convex cone. So a cone, topologically a cone is just it's pretty obvious thing because if you just multiply it by constants, right, it's still a member of this. Convex cone, right? It's a cone because it just you can multiply it. You have a point here, and you multiply it, it's still on the cone, right? So it's a fun fact, I think. You see convex cones, cones are like convex spheres and a lot in topology, if you like topology. I know what you guys like. But yeah, and these are pretty interesting topics we'll talk about in a second. If a member of these, right, so a member that can be expressed as x star or x star x, is what we call confusingly non-negative. A term that will become apparent in a second is how I can call a term in a vector space which is not ordered negative. Remember the pain of having to try and prove that the complex pain, the complex numbers was in that order. These are
Like where all where this. Like R is ordered.
yeah, R is ordered, C is ordered. And
Oh, and also, what was the bracket there?
x star.
Yeah, what was the bracket? Is it
Which is the set of x stars.
X
X star. So if you want it for completeness, there's x star such that x is a member of the algebra.
Okay.
I just never like writing the talking instead. We're actually going to do something annoying again, and as I just said, there is no order on algebra, just like there's no order on C, just an order on matrices. But we can define the partial order on standard Jordan elements, right? So the set of x such that x is self-adjoint does actually have an order. But for the order to be apparent, we need to create, I think, our last definition. And this is a nice topic which I recommend you take in 4th year, spectral theory with Panofsky. I did it. It was just meeting one other person. It was great. It's 3-hour-long seminars.
Definitely take that one.
Yeah, we might be there as well.
Yeah. Good luck.
Yeah,
Oh, it was very nice.
really.
We actually in a lecture theatre, just 2 people
Yeah,
on a lecture.
that's a few of you.
Yeah, just three of us.
In a lecture theatre.
It wasn't actually that God. It was in a room with the IOE, but still. Anyway, you remember eigenvalues, right? Eigenvalues on matrix operator. An eigenvalue is just how do you work out an eigenvalue? This is like doing that. You take a minus lambda I, take the determinant, you solve this, you know that, but you want this to be 0, right? So you want this, of course, you want this to be non-invertible, right? 0 non-invertible. Determinants are all lambdas such that this new matrix is non-invertible, right? We're going to do something fun, and we're going to replace f with an arbitrary operator, right? This is the identity operator on H, right? We're going to work with BH, actually BH. We can work with general linear functions, the linear operators, but this will be BH, right? F minus lambda I, this is also a bounded thing, pretty easy to say, because it's closed under vector operations. F minus lambda I is an operator, and when this operator is not invertible, or lambda in C, such that that's the case, this is called sigma x, sigma f. But we're just going to use x actually here. Operator is x because x, and the x is in a bounded operator. Sigma x is all lambdas such that this new function is non-invertible. This is what's known as the spectrum of an operator x. In spectral theory, we're working with that. Now, notice again, I mentioned before, eigenvalues, right?
Wait. Is it for example?
No. X is bounded to algebra, bounded in H, B on H, bounded in the operator in H. So eigenvalues, again, this definition of eigenvalue is non-invertible. If H here is finite dimensional, then this is just a set of eigenvalues. If it's infinite dimensional, annoyingly, set of eigenvalues denoted sigma p of x is actually just a subset of the spectrum thereof, which makes you want to cry, but and it does have to be shift normal sometimes. That was illustrated. Oh, P stands for point, the point spectrum. But you don't need to do this. It's no relevance what we're talking about later on. The point spectrum is just the set of eigen values, or specifically a set of all points x. There's a point lambda in C, such that x. Okay, this is confusing. I'll go back to f. Fx equals lambda x. You know the definition of eigenvalue. Fx lambda x, right? All set of lambdas. This is what this means, right? But it turns out these aren't necessarily equal.
Take the full field module.
Take the full field module. It's to do with the fact that when you make H infinite dimensional, you can't get a basis. You can get a basis. You can't really define a basis like you did in finite dimensional cases, right? And the way you use eigenvalues kind of needs a basis, because you want an eigenvalue basis. But if you ask me afterwards, I will find an example. Come into my head. Rather complicated examples, but I'll think of an example of something which isn't equal. Yeah, this is just to make sense of it. You don't actually do that. This is the spectrum of an operator. Yeah. Okay, we're gonna. I was always so annoyed when professors would just assume more and more structure on things. Like assume this has, it's nice, but well behaved, it's continuous, commutative, all that. No, I quite like it because it allows me to simplify things. We're going to look at a specific case of this algebra, a commutative. Again, I'm going all over the place, but I will build up something, I promise. A commutative C star algebra, so it's this algebra such that it's commutative. So every point x star. So x is normal as well, but yeah, so just x, y equals y, x, commutative. Nice to behave, does some nice things. We're going to define a new cis algebra, which will be a commutative cis algebra. There's not really much difference from the general definition of cis algebra and commutative, well, in fact, it's commutative. We're going to find a very useful case, which actually will be a bit weird to think about first, but we'll take X is a topological vector space, topological space, as our topology is, yeah, topological, it's topology, right? So it has a moment of topology. If you want to ask it later on, yeah, it's X is Hausdorff. From Hausdorff is. Yeah. Any two points have distinct open sets around them. It's Hausdorff. It's locally compact. You guys know what compactness is. Jolly good. But very simple. Every point has a compact neighborhood, right? Sometimes you have locally things which is very complicated to talk about, but every point has a compact neighborhood. And we're going to denote C0x as the set of continuous functions.
Yeah, that's
Yeah, continuous functions from x to c that vanish at infinity. Using space correctly. Vanish at infinity, which you guys know what vanish at infinity means, right? The real line of distinguishing infinity. Oh, yeah. As soon as I tell you, locally compact. As soon as I tell you what vanishing at infinity means in this arbitrary topological space we have here. The real line just means, you go to infinity, infinity. But what does it mean? What does going to infinity mean on your space? I really shouldn't productize so much. What it means is that typical analytic definition for all epsilon greater than 0, there exists a compact set, right, in X, such that the function here, say f of X, from thereof, is smaller than epsilon for all X outside. For all X outside of the compact set. So, again, you've got your space, you've got your function on your space, right? And you want so that for every epsilon, you can create a large enough compact set such that outside of this compact set, the function is below some sort of point, right? It's a weird way of thinking about punishing infinity. This is what it means. If you take X to be complex, real numbers, right? Or complex numbers, you can just take real numbers, you can just take a function such that this works, right? It doesn't have to be homomorphic. Homomorphic, it's analysis, the complex analysis, then just forget all that. If you want an example, I don't know. F of X equals, or F of Z equals 1 over norm Z, which is 1 over Z. That obviously goes to infinity.
Or yeah, on R, e to the minus x on R.
R e to the minus.
No, e to the minus x on R.
X over R.
Exponential of minus x.
Exponential of minus x on R. Then we are like.
Oh yeah. But of course we want to go to C. So I mean, it's on C. It goes to C, right? Or minus x squared, actually. Because you want it to go to infinity on both sides.
We let it just be 0.
You can actually it's trivial, but it works, It's not even a non-trivial example. Really happens.
0, then you may not be.
But we'll give that distinct a bit of choose. But this also is a C algebra, and more broadly, it's a commutative C algebra. Because multiplying functions pointwise works. And of course, the commutativity lies from the level of compactness. Of course, X is an arbitrary vector space, and we will talk about this in a second with a much worse behaved X, which will be fun, I guess. And this is where it gets into the algebraic side of things, commutative algebra. If you do commutative algebra in X or representation theory, one of those things in third year, then guys will be learning about this.
Yeah.
Oh, we're going with little weird topics, you'll find various basic mathematics. I'll be mixing out there. Okay. Representation of things. When we in maths, we have all these different structures, vector spaces, things like that, but we don't really know how to represent them in certain ways. Which are bases and vector spaces, represent numbers, and some things said in group theory. But this is going to be an abstract representation. Okay. Gelfand representation. Our aim, and I hope I get this to the end, is to show why an arbitrary C algebra, anyone, is going to be equivalent to a subset of linear bounded operators. Now, an analog of this, which, if you remember correctly, was called the theorem in group theory, where any finite group is isomorphic to a subset of the symmetric group. Cayley's theorem, which is a pretty cool thing, right? You've got this group is isomorphic to a subset of a fixed group, right? Now this is nothing to do with it, it's just like a comparison, because this goes to the third. It says this algebraic structure, this algebra, is always going to be not even isomorphic, isometrically isomorphic to a subset of this. And this is what we're going to show. I think this will more after that. But and of course, which means that once you work with cis algebra, you're actually also working with linear operators.
So we just work with so everything in C algebra will be translated.
Yeah. Because the way I would really use it is using cis algebra to understand linear operators. That's more what I've been learning from algebra. It gets used quite a lot, I think, in fields from mathematics. I mean, oftentimes the way you prove things is to look at a different, completely other fields. It wasn't how they proved the Fermat's last theorem to look at the elliptic curves or something.
Yeah.
From known theory or something. Yeah, well, you know. No. Okay, so representations. Important things. We make this, we're going to take A here, do some blue now, to be a commutative Banach algebra. Right, so it doesn't have an involution. And of course, when we redefine a representation of this, it's just the same thing on C algebra. Banach algebra, right? We also make this over complex numbers because I like working in complex numbers. So, first thing, a non-zero homomorphism is from A to C is called a character. Okay, just definition of a homomorphism because it's an algebraic homomorphism. Right, so it's what I defined before. It has linearity, multiplication works out. It's a homomorphism on the algebra. Because it doesn't have the involution property, but homomorphism, it's called a character.
Yes, the one in algebra.
Unfortunately not.
But it's the same name.
It's the same name. There'll be a lot of things with the same name soon now. I'll come back to that. Yeah, we can do sort of standard tricks you do when you try and shift between areas is to redefine things in a different way. So given an A in the algebra, we're going to find this function, A hat, to go from phi A here being the set of all characters, right? Phi A equals set of characters. The characters, of course, it's C, right? And define the phi hat of a character is just the character evaluated on A, right? So these are actually equivalent. basically talk about it. This is a trick you see a lot, coming up a lot actually in higher level mathematics. 7 characters. By the way. Now, a hat is continuous in a topological sense. You guys will continue to do this topologically. So the pre-image of an open set is an open set. Yeah. We don't know sense. It's continuous topologically. And it vanishes at infinity. Like we said. Because I'm not going to prove this, but set of characters, right, is Hausdorff, it is locally compact. Proof of thing. I don't know, we're very technically on compact, continuous functions. And we can also prove that it vanishes, a hat vanishes at infinity, but only under a certain topology. Space. Under a certain topology, because of course you choose a topology called the weak star topology. And the definition is quite a often you define topologies to mean the weakest or the coarsest topology, but in this case, the weakest topology, right, is the set of open sets, right, such that f of x, right, in fact, essentially dot of x, right, from x star to c. So it takes a functional in x and dual of x, right, applies it to x, right, into c, right. Weak topology is defined as a topology such that this function here is continuous for all x and x, right? Very weak definition. It's the smallest topology possible, such that this holds, right? Of course, the small topology is obviously it's a trivial topology, then you've got maximal topology, and somewhere between it's the weakest topology. And under that topology, this vanishes at infinity, which means, of course, that we have the set thereof is a C-star algebra, and of course, we can, of course, not an easy mapping from A to a hat, right? Just define a hat as we did beforehand. A to a hat is a function from the algebra into C0 of the set of characters. Yeah. Characters because a hat it maps a character to C. Its function there is continuous. And this is what's called the Gelfand representation, because it associates every point of the algebra with a function which maps homomorphisms to C. An analog of this would be to take the dual space of the dual space. And you've got this space, the dual space of the dual space, and you can actually identify every point of the vector space with the dual space, with a little point in the dual of the dual. Again, pretty easy to do. So, yeah, so this is the definition of the representation. It's a way of associating every point of the algebra with a point in C0 of set of characters. Now we should do this on Banach space. We can pretty easily add, make it C algebra, definition is still the same. An example actually of this would be if you make A equal to C0 of an arbitrary space of X, topology space X, which means that the representation is just like is from C0X to C0 of C0 of X. But this actually has pretty nice properties because in here the characters was fine instead or bar fine. Characters on F is actually just fx, fx f dual. It's just an example of representations. So there's representation in here. Okay, let's go back to the spectrum. Spectrum is a algebra, right? Define as such. The spectrum A hat, big A hat, equals the set of non-zero star homomorphisms That's it, yeah. Homomorphisms, on A. A to C. Yeah, I just see. Now, of course, earlier we defined another spectrum, which was the set of complex numbers with non-invertibility. With this spectrum, which is a set of homomorphisms, and they are not related. I don't know. The other name of this is a Gelfand space. I mean, again, I'm lying, but there is one relation between the two of them. If you take X in A, right, then the spectrum, normal spectrum, right, so in not lambda such that X minus lambda I is non-invertible, it does equal the evaluation of X, on X, the evaluation on X of all homomorphisms in the spectrum, only if A is commutative and unit, so it has a unit. Right, because it's doesn't have that unit of X doesn't have units. This is the one relation we have between the two of these. Which is a thing. Another thing. It's another fun thing. The analytic notion of sort of eigenvalues of a function equals the evaluation of homomorphisms. Remember what I've ever seen homomorphisms and eigenvalues in the same sentence or even page. Now, spectra have a property, they are bounded. Again, I think of one spectral theory, they're bounded, and we call the supremum of all, lambdas, lambda in the spectrum. The supremum of all numbers, of the mod, absolute value of all numbers, is called the radius of X. And using something called the spectral radius theorem, which you can actually compute this very easily, spectral radius theorem, we can give additional properties to A hat, the spectrum of the algebra, which is that A hat is locally compact, it's Hausdorff, and A is contained within the unit ball of the dual space. Was the norm being standard operator norm on the homomorphism? This homomorphism is also an operator, linear, on the vector space component of the C algebra. Again, you see, it's all very here and there, very complicated stuff. So now we're going to give a first definition of our sort of end results that we are looking for. Whether we want any algebraic C algebra to be isometrically isomorphic to a subset of the bounded functions, the bounded operators. Things like it's a lot easier to do this when it's commutative. So we give the first statement, commutative Gelfand line mark. Gelfand line mark is the theorem, name of the theorem. We're going to show again. The commutative version of Gelfand line mark is actually formulation is different from what we're going to have here. But formulation is, so we're going to let gamma from A to C0 of A hat. Okay, because A hat also vanishes in infinity. We can show this. So we can, and it's locally compact Hausdorff, which means we can, it's part of this C0 A hat. So gamma is takes a member of this algebra and brings it to the homomorphisms of homomorphisms, which vanish at infinity. Then showing that this is a homomorphism isn't that hard. Just follow the definition of homomorphism, plug in, right? Bijectiveness follows from our Gelfand representation because the characters so when we're in C-star algebra, right? The homomorphisms have to follow the involution property. That's the involution of the image. The image is the whoever it is, which means it's a star homomorphism here, and we can show that this is so this is a star homomorphism. But even more, that is star isomorphism, which follows from the commutativity property. And that's actually sufficient because it's star isomorphism. It's isomorphism, so it's bijective. It's bijective, so it's injective. And an injective star homomorphism, as I said beforehand, is an isometry. You know what isometry is as well? It just, the lengths stay the same, kind of thing. So the statement of the theorem is just let lambda gamma a of this, then gamma yes, this is the Gelfand representation. Yeah. Then gamma is isometric isomorphism. Apart from the commutativity part, which again I'm not going to prove because I'm sure you'll have, but I'm do like half past or
Now it's like 1.
yeah, so I'll leave that up. You can come ask me afterwards. I can try and show you this, but it's commutative, which means it's isometric star isomorphism. Now this is actually an analog, because again, a homomorphism is also an operator, right? And this vanishes at infinity. So we have this, sorry, not equal. This is actually a subset of bounded, which vanishes at infinity must be bounded. Doesn't homomorphism vanishes at infinity. The function, anyway, trust me, it's part of BH. So it's isomorphic to a subset of BH. And also, a closed subset. This is a closed, it's a closed set. So it's a closed subset of this, right? This is the commutative part of it. I'll see if I can get the general part, which actually just removes the commutative side of things. Using another little thumb tool we have going for us. Now, this is going to be what you're going to do if you're doing representation theory as a module. Next up, we're going to use what's called a GNS or Gelfand Nymark Siegel construction, which is how we're going to represent a non-commutative algebra, because the commutativity property gives us all sorts of nice properties which allow for things to work, become isomorphic in the end. There's also a way of representing non-commutative like things. So we had a Gelfand representation, right, which is between A and C0 of A of a set of characters, or indeed this here, Gelfand representation. Now we're going to talk about a star representation. Quick thing, star representation of A on a Hilbert space H is a function pi from A to B of H. So we're going to straighten that. Of course, C-star algebra, T-star algebra. We can define this as to bring homomorphism. So it's an algebra homomorphism. Non-homomorphism is a homomorphism, even a star homomorphism. Such that pi is non-degenerate. Not spelled, but I'm a mathematician. Non-degenerate, which also means, of course, non-degenerate means that the set pi of x psi for all x in A and psi in H. So x in A gives us a bounded operator, and we just evaluate it on psi in H, right? The set of this is dense in H, right? This is what non-degenerate means, and such a thing always exists. That's what is what's called the star representation of A on H. course, you could be the trivial one. You know, the once you zoom onto this, you can take anyone you want. And we're doing something else. Something called a state on A, right? Simply enough, it's a functional A prime in a dual of A, right? Such that the operating norm of F is 1. State. And if any do quantum mechanics, this comes in a lot. Yeah, we need that. Final bits. Before we start our nice. So pi for our representation, sorry, for pi. So which one? Norm F.
Yeah, what about,
Sorry?
what does that equal to?
Norm F.
Yeah, sorry, I just can't quite read your hand right
Oh yeah, no, so I mean, I want you guys handwriting. Yeah, norm F, so it's the operator norm. So again, F is from A into C, right?
now.
And the norm of F is we basically just want the property that for any x in A, f of x, the norm of that, is always going to be smaller than x. That just means that the operating norm of x. So given pi, our representation, and novel representation, take some A in our algebra. This A is called a psi in H, not A, psi in H. This psi is called a cyclic vector. Cyclic vector if pi of x on psi for all x in A is what's known as norm dense. So instead of density in the topological sense, right, we should mean that the norm of the vector we get here is dense in R. Yeah. Take norm, or you take the setting norm of everything, dense in R, it's norm dense, right? And if so it has that property, it's called a cyclic vector. Now, we're doing that. Now, I said things. I said a representation about states. Pi is a representation, and take so it to be a cyclic vector. Then this function from A into the norm, the inner product pi A psi and psi. This actually satisfies the property of being state. Its norm is 1. This is a state, right? So which means that given some representation, right, the representation is equivalent to a state. Furthermore, we can say that conversely, given some f, there exists a subrepresentation pi of f such that this holds, and so does this. So again, representation and again a algebraic thing, homomorphism stuff, and our state is just a function. Lots of connections between these. And then now we can come on to the what I call the general Gelfand Nymark theorem. which states that given a C star algebra, that A is isometrically star isomorphic to a subset of BH. So the theorem I stated at the beginning, and yeah. It's a very important theorem because whenever you're working, again, if you're working just in algebra or just an analysis, you might not have heard of it. But this is one important because it links together this idea of 6 algebras, which are some of the most important types of algebras actually, and the use in quantum mechanics, as I mentioned before. Quantum mechanics is basically just based on this idea of 6 algebras. Right? You will learn about it in physics because you want to understand this. But in theoretical physics, the manipulations of 6 algebras and knowing how they work alongside linear functionals, because quantum states are linear. Superposition, remember all that? We did physics. It doesn't matter. But yeah. And the proof of this is really not that hard. It involves a lot of theorems. And actually, I'll probably show that out in 2 minutes. Okay, so here's how it goes. States of F, right? States of F, they exist. There are states in F. States F, there are states in A, right? We have states, right? They actually form a convex set. You know what convex is, right? Convex set. Which is nice. Now another theorem, the Krieg-Milman theorem, states that for every convex set which is locally compact Hausdorff, right, which this is, there exist things called extreme points, right? Extreme points being points that don't lie on a line between 2 points, right? So like corners, for example, corners are extreme points because they don't lie on a line between 2 points, right? Just a trivial line between 2 points, right? So these called pure states, which in quantum mechanics are states which are non-entangled, but pure states, right? F, right? So with each F of these, which is each F, we have the representation F, right? Now we can take the representation direct sum. I'm just going to shoot through this now because I don't understand that. Representation sum F, which the definition is actually not hard, it's just pi of x, the sum over H of the Hilbert space F equals the sum of pi Hilbert space F. You can also do this again if you want. Yeah, fine. And by the Krein extension, so the Krein extension, these things F, right? Whenever you take them on a form of a joint, in a joint form, right? These will be greater than or equal to 0 because they first of all they will lie on the real line, right? And they'll be greater than or equal to 0 on anything which is in this form, right? As we said before, non-positive things on the cone. Yeah, and then we have one quick equation. It goes like this. You've got some F, pi of F of x, right? Pi of x on some psi, right? Pi subscript F, right? This takes it to into the functions that you just into bounded. X is in A, this brings it bounded on H, and applied to some vector in H. This equals, definition-wise, fx squared swap f pi f x psi pi f x psi. Now this is some of the properties of the of the homomorphism. So the homomorphism actually forms a self-adjoint space. So we can swap it over by, for instance, the introduced property. If you take the adjoint, you have to place the adjoint in pi f x on psi, which equals psi, what lines? Pi f x x psi x star x by the properties of the homomorphism on psi, which actually happens to equal f x thing x star, which is greater than or equal to 0 because we're using a pure states f. And this is actually non-negative, and it only equals 0 when it's truly 0. So when x doesn't equal 0, it doesn't equal 0, which means that pi of f on x is not equal 0. And since we define our new pi, right, our total representation as the thing over all states, this implies, and because it's not equal 0, so it implies x other things will be 0. So it's a kind of multiplication type thing going on. Pi general x does not equal 0. So no pi is trivial, which means that representation homomorphism is injective, which means that it's injective, it's isometric, and with injective, it's bijective to some subset of its image. And that is, I think, how the theorem ends up. You've got A, use some shenanigans, take F pure states, bit of algebra here, show that it's injective, it's isometric, it's isomorphic, star isomorphic to some subset of BH. And that, I think, is the theorem. And this is also my time. So let's let me ramble on about this for half an hour and a half, and for saying through it as well. This one.
Any questions?
Any questions yet? By the way, you can't say I will be around here afterwards, or not. Yeah, I went very quickly through a lot of things. It's all complicated. I didn't understand everything. Don't worry. I didn't until 2 days ago. So I'm like, it was yesterday.
Yeah, right. Any more questions?
How did you find out about this? Like, it is something you studied during your degree,
Well,
or did you just?
I did spectral theory
Okay.
last time. We don't talk about this, right? But then I ended up getting a short course on spectral theory, which is the textbook we had.
Is it like compulsive, like the first year with hierarchy?
Basically, yeah.
He likes his textbooks.
He does like the textbooks. There's like another one, but it's like good. I think it starts straight by talking about C-star algebras
Oh, nice.
before you even get anything spectral. And the spectral thing, it's the fun thing is really the spectral thing. Anyway, so it's like this. I basically went through to try to understand how they acted, and that gives me the same author an invitation to C-star algebras,
Nice.
which I then read as well.
Have you bought the book now next to you?
It's they're the same book, honestly. Have a lot of the same material. And also, I never did like proper algebra.
Oh, so you haven't done basic algebra courses?
I've stopped at algebra 4.
And then in year 3, did you take functional analysis?
No.
To ask about the more.
This is functional.
You should do functional analysis. It's pretty good. I think it's pretty good. I didn't do it. I just learned it. So I had to have as a prerequisite to do spectral theory. So I taught myself it during the summer to do spectral theory afterwards.
So basically, you haven't done any analysis like measure theory.
I've done measure theory. I
Okay.
didn't do the course. You can study in your own time.
Yeah, well, that's part of it.
I learned measure theory with Big Gordan. You know Big Gordan, right? You know Baby Gordan.
Maybe you lose it.
Baby
Okay.
Gordan, which
The principles of
there's also Big Root, which is real complex analysis.
really complex now.
Yeah.
We did have this.
No, it's very good.
Yeah, it's also measure theory.
No, the way Rudy treated it for the one is that he defined like all the measure first, and then study the real analysis, and then use the compact method to do the compact analysis, which is not how things are done here, or how things are normally done for like a typical.
Yeah. I remember when we were doing measure theory. Measure theory is pretty fun. If you do anything to PDEs later on, if you do spectral theory, he does recommend. Panos does recommend you do measure theory, even though he did not use it at all.
So actually, what model does he use
He,
for spectral theory?
you want function analysis, right?
For function.
Function. It says on the website you prerequisite the function analysis measure theory, and I think like multivariable.
You need multivariable.
Yeah, exactly.
Multivariable is not helpful.
There's no forms here.
Yeah, but
No.
you actually need it. Like, or can you take the model and like define problem?
You should, if you could probably take function analysis. You need to know function analysis, right? Like he does not want to teach you function analysis. You need to know it. You can teach it yourself. It's not that hard. I remember a good book if you want it. If you want a title of book and
Yeah,
name.
because I'm like maybe thinking next year or not, because I want to do spectral theory.
You can just take it.
Yes, but I have, so guys, it's a problem for me. So I have only 3 options, and it's very hard to choose.
You're doing 3-5.
No, because I'm doing econ, so I have one module done already. So I can choose only 3.
Yeah, just take spectral theory, like, next year, and just self-study all the function analysis.
It's not too much.
Yeah, that's actually fun.
Yeah. But if you want to, if you want to do spectral theory,
I understand.
don't bother to if you do next year.
No, maybe year 4.
Then if you don't year 4, then just do function analysis next year. Or just learn it. Again, it's not too different from. It's as hard learning function analysis as it was learning linear algebra at university level.
Yeah.
Oh, okay.
I mean, there's only like 3 or 4 main theorems.
Yeah, representation, Lax, Milgram, Hand-Bannock.
Yeah, and then the rest are like, human space analysis, orientation.
No, sure, that's just
Yeah, so it's like not actionable.
Also, you spectral use like what's it, low toplet spaces, one Neumann hot spaces, all manner of fun things. Hilbert Schmidt spaces, trace class spaces.